Ladies and gentlemen, I'm delighted to be here with you today. We are here to delve into a topic that is both profound and challenging, the hat trick exploit Chrome twice from runtime to JIT. Before we delve into our main topic, let's start with introductions. First, I'm Wang. Nan is respected security research at the 360 Vulnerability Research Institute. In the past 2 years, I'm ranked among the top 10 Chrome VRP research, and I was named the second-ranked Facebook White Hat in 2023. Next, we have Zhenghang Xiao. As an independent security research, he primarily focuses on browser security and will be pursuing the master degree in the field. Next, this is the organization we represent, the 360 Vulnerability Research Institute. We are here to share our insights and discoveries, hoping to make the digital world safer.
Hello, I'm Zhenghang. To ensure everyone has a clear understanding of the talk, let's take a look at our agenda. We will start with a brief introduction, providing an overview of our research targets. Then we will proceed to share the details of 2 remote code execution vulnerabilities that we have discovered. And finally, we will conclude this talk with a live demonstration. Now, let's kick off with the introduction. The Chrome browser adopts a multi-process architecture. This design divides the browser's tasks into different processes that run independently. Key components include the browser process and the render process. The browser process is responsible for handling the user interface, interacting with the operating system, and managing other processes. On the other hand, each render process operates within a sandbox environment to ensure security and manages individual web pages. In our research, we primarily focus on the render process. This is the component that directly handles external inputs and is therefore an important target for potential security vulnerabilities. The V8 JavaScript engine, as a crucial component of the render process, possesses a complex and intricate architecture. This has garnered extensive security attention, and due to the flexibility of the script engine, it is prone to exploitation by attackers. Our research primarily focuses on the runtime component and the Maglev optimization within the V8 engine. These 2 areas provide abundant opportunities for vulnerability discovery and form the core content of our presentation today. In the next section, we are going to share our first remote code execution vulnerability, which is the focal point of our discussion today. This vulnerability is associated with an incorrect implementation of the new JavaScript engine in the V8 runtime environment. JavaScript Promise is a mechanism used in JavaScript to handle asynchronous operations. A promise object can be seen as a commitment to perform an asynchronous operation, indicating that it will be completed and return a result at some point in the future. It can have 3 states: pending, fulfilled, and rejected. Once a promise enters the fulfilled or rejected state, it is considered settled. When working with promises to handle asynchronous operations, we can register callback functions using the promise.len function and the promise catch function to handle both successful and failed operations. The promise.len method is used to register a callback function to handle the changes of promise states. It takes 2 callback functions as parameters. These functions will be called when the promise is settled, and they will receive the promise result as an argument. This slide presents a JavaScript example that utilizes promise. In this example, we first call the fetchData function, which creates a promise object with an asynchronous operation. Then we use the len function to register callback functions that will be invoked when the promise's state changes to either resolve or reject. In this way, when the asynchronous operation completes, the code inside the asynchronous function will call either the resolve or the reject function based on the execution results, thereby updating the state of the promise object accordingly. Once the promise object state changes, the onResolve callback function is called to output the value returned by the asynchronous operation. Promise.any is a static method of promise. It accepts an iterable object, usually like an array of promises, as an argument, and returns a new promise. This returned promise is immediately resolved as soon as any one of the promises in the iterable is fulfilled. If all the promises are rejected, then the returned promise is also rejected, and it includes an aggregate error object that contains the errors from all the promises. The whole is an internal sentinel element within V8. It is distinct from undefined or none, as it represents an absence of value, meaning no value at all. Let's consider a JavaScript example here. We first create an array where the second element is left without any value assigned. When we call debug print on this array, you can see that the elements array contains a value referred to as the whole. Now, let's dive into our first RC vulnerability that we have discovered. On the left part, we have the standard definition on Promise.any in ES6, and on the right, we have a proof of concept of the vulnerability. Let's first try to understand the standard execution flow defined on the left. Initially, the Promise.any function declares 3 variables. The arrow variable is an array used to store reject values parameters when all input promises have been rejected. The remaining elements count represents the number of input promises still in pending states. The last variable, index, represents the index of the input promise being currently iterated over. Then comes the loop. Step A to D. The Promise.any function repeatedly fetches the next input argument from the iterator. If the next element is not null, an undefined value is added to the arrows array as a placeholder. In step E, it attempts to call the promised resolve function to wrap the promise object currently being iterated over, ensuring that the returned result is a real promise object. This is because the argument passed might not be a valid promise object, but could be a constant like a number or string literal. In step F and G, the Promise.any function dynamically creates a built-in reject element and stores it in the onReject variable, while also setting some property values. In step H, since the Promise.any function has successfully obtained the next input promise object, the value of the remaining element count is increased by 1. Finally, in step I and J, the len function is called on the input promise, setting the callback functions that need to be called after its state changes, and the index value is updated. The entire execution flow can be mapped to the sequence number of the proof of concept on the right: 1, 2, 3, 4, and 5. One important thing to note is that the proof of concept calls the call function on the Promise.any function, causing the Promise.any function to be called within the context of the craft promise function that is passed in, and the type of the value returned by Promise.any is craft promise. The craft promise function itself is called even before the first step of Promise.any. To obtain the functions to be called when this craft promise instance is resolved or rejected, such as the result capability resolve. or reject in the Promise.any standard. Now, let's delve deeper into Promise.any. When any input promise is resolved, that promise will immediately call the resolve of the final returned craft promise, and the whole process ends. However, when an input promise is set to reject, Promise.any does not wish to interrupt the execution flow of the remaining promises, because there is still a possibility for the remaining input promises to be resolved. Therefore, when an input promise is set to reject, the callback function it will call is the dynamically created onReject function, not the reject function of the final returned craft promise. The standard of the onReject function is shown on the right half of the slide. It first retrieves some attributes previously defined on the onReject, including the index of current promise, the errors array of the current promise, and the value of remaining element count, and so on. Next, the onReject function stores the value of the current promise that it has been set to reject in the errors array. Finally, it subtracts 1 from remaining element count, updating the current number of promises still in the pending states. One thing to note is that when executing Promise.any, remaining element count is initially set to 1, and only after the entire Promise.any function has iterated through all inputs does it subtract the initial value of 1 in step 4bi. This is done to ensure that during the execution of Promise.any, when some input promises are set to reject, it won't trigger the condition in the reject element function, where remaining element count is compared with 0 and return an aggregate error. This means that Promise.any does not prematurely set the status of the returned promise to reject. Only after the entire Promise.any function has been executed does it become possible for step 8 in reject element function to be triggered. Now, let's briefly focus on the errors array. For a standard, we can see that for each input iterated by the Promise.any function, an undefined value is added to the errors array as a placeholder. Then, when an input promise is set to reject, the corresponding reject value will be stored in the errors array. So, how does V8 handle the errors array? We can see that in the implementation of the Promise.any function, V8 does not use undefined as placeholder when iterating over new inputs. Instead, it uses a lazy initialization approach, leaving the initialization of errors until the first rejected input promise calls the onReject function. In the implementation of Promise.any reject in element closure, we can see that the capacity of the errors array is influenced by two variables, remaining element count and the index. However, as we explained before, during the execution of the Promise.any function, the remaining element count will be one larger than the actual number of inputs that has been iterated. This means that if an input promise calls onReject during the execution of the Promise.any function by V8, the newly created errors array will be one size larger than the actual number of the input promises. And the extra empty spot holds the initial sentinel value, the whole. This enables us to extract the whole value from this extra space for subsequent vulnerability exploitation. Exploiting the whole for remote code execution is not uncommon. Several wild zero-day vulnerabilities take advantage of the whole for their exploits. So how can we achieve renderer RCE from the obtained whole value? This brings us to the structure of JS map. Let's dive deeper into how JS map handles the whole value. When the map delete function is called in the JS code to attempt to delete a key value pair from the map instance, V8 first searches for the key to be deleted on the map and marks the found element's key and value as the whole value. Then it updates the number of current elements and the number of deleted elements. Lastly, it checks whether the number of remaining elements is less than half of the number of hash buckets. If so, a memory shrink operation is performed. So how can we take advantage of this feature? The left slide shows parts of the exploit code snippets that can construct a map object with a size of -1. The right side shows the data changes in the internal map structure after each step of JavaScript code execution. Each element is composed of 34 bytes data, representing the key, the value, and the index pointing to the next element in the element linked list. After calling map set 1 and 1, the total number of elements will change from 0 to 1 due to the increase of elements, and an element will also be placed in the space behind for storing elements. Next, we call the map set function. Try to store the whole value in the map, and then we try to call the map delete whole to delete this whole value. Since the whole value is indeed on the element chain, the number of elements in the map will decrease by 1, and the key value pair of the deleted element will be set to 2 the whole values. But note that the deleted element will not be immediately removed from the map, but it will still exist in the map. Next, we can try to delete the whole value again. The operation executed internally by the map is the same as above. It will update the total number of elements to 0 and trigger the shrink operation to completely delete the deleted elements on the linked list. But what we need to be noted here is that at this point, the total number of elements is 0, but the element pair 1 and 1 still exist in the element array. Therefore, we can continue to try to delete 1 and 1 elements next, which will change the total number of elements to -1, and trigger the element shrink again to release the whole key value pair set when deleting the elements. So how can we use a JS map with a size of -1 to achieve out-of-bound operations? Because JS map access the index of elements when setting a new element is by adding the element count and the deleted count. And at this time, the result is -1. This makes that when we try to call map set to set a new key value pair, JS map will write the data out of bounds forward. This will allow us to modify the bucket count attribute at will. When we can control the bucket count, it becomes easier to write out of bounds because the element-based address when JS map set a new element is obtained by adding the start address of the bucket array to the bucket count. As long as we modify the bucket count to be larger enough, the next time we execute the map set function, we can write out of bounds in the far distance to the back, modifying the carefully arranged JS array structure behind the JS map structure, so that the length of this JS array becomes super large, which is convenient for the subsequent construction of arbitrary address read-write primitive, and then achieves the purpose of remote code execution. Next, we will share our second remote code execution vulnerability. This vulnerability involves the new compiler, Maglev, being implemented in V8, as well as the classic garbage collection vulnerability pattern. There are several well-known compilation mechanisms in V8, including the ignition interpreter, the Sparkplug compiler, and the widely known Turbofan compiler. Maglev is a newly implemented mid-tier compiler between Sparkplug and Turbofan, which aims to compile code as fast as possible while allowing for some level of optimization. In JavaScript, many objects have short lifetimes and quickly become garbage. By dividing the heap memory into the young generation and the older generation, it is possible to focus the garbage collection process on the short left objects in the Yang generation without globally scanning the entire heap. This significantly improves the efficiency of garbage collection and is known as the generational garbage collection. The Yang generation is where newly created objects are stored. Its characteristic is that the objects have a short lifespan, and most objects quickly become garbage. To enhance efficiency, JIT employs a garbage collector called a scavenger to reclaim memory occupied by objects in the Yang generation. The scavenger utilizes a copy algorithm and divides the Yang generation heap into two spaces, front space and the two space. During the garbage collection process, the surviving objects in the front space are copied to the two space, and then the front space is cleared. This enables the rapid collection of a large amount of garbage objects. The older generation stored objects with longer lifetimes. When an object survives multiple Yang generation garbage collections and remains live, it is promoted to the older generation. These objects have longer lifespans and are less likely to become garbage. When discussing generational garbage collection, there is a specific scenario that requires special attention. It occurs when the garbage collector decides to free content in the Yang generation, and there is an object within it that is referred by an object in the older generation. If we attempt to free this object, it would require traversing the entire older generation, resulting in a significant performance overhead. To address this issue, generational garbage collection introduces the concept of a remembered set. Each time an object is updated, a remembered set is used to keep track of the references from old generation to the Yang generation objects. In other words, the remembered set actually stores pointers to the old generation objects. To correctly record the remembered set, garbage collector introduced the concept of a red barrel. The red barrel is a set of special code snips that handle the updates of remembered set. However, if the execution of the red barrel is omitted during the process of updating pointers, the garbage collector may not be able to find the reference from the older generation object to the Yang generation object during runtime. This can lead to incorrect free of the object and result in a use after free vulnerability. Next, we will share the relevant information about the vulnerability we discovered. The code snip above represents part of the proof of concept code. In the function f, a parameter a is defined, and based on the value of a, the variable phi is assigned a specific value. Then a bitwise OR operation is attempted, and the resulting value is set to the property C of that parameter. The Maglev graph is relatively easy to understand. The number at the beginning of each instruction represents its ID, and the arrow and the letter X following the instruction indicates the output value of that instruction. For example, N13X represents the output value of the instruction with 13, which is a constant object. During the process of generating the Maglev graph from bytecode, Maglev passes the bitwise OR SMI opcode and generates a checked SMI untagged node to ensure that the output value is a SMI value, which represents a small integer. Therefore, when Maglev continues to parse the set name property opcode, the previously generated checked SMI untagged node restricts the value to be stored as an SMI. Therefore, Maglev generates a stored text field no right barrel instruction, which omits the right barrel to speed up the execution when saving the value to a variable property. Once the initial Maglev graph construction is complete, Maglev attempts to perform an optimization mechanism called phi untagging. To be conservative, During the initial graph construction, Maglev ensures that every file node is a tagged file, meaning that all inputs are required to be tagged and the output value is also tagged. However, in certain cases, having file nodes as tagged types may result in additional tagged and untagged operation, which can lead to performance overhead. Therefore, Maglev considers optimizing some tagged file nodes to untagged file nodes based on their inputs. Returning to the Maglev graph related to the vulnerability, file untagging involves handling the input and output nodes of file nodes. For the slides, we can observe that the file nodes undergoes changes before and after the file untagging operation. Its inputs originally coming from tagged nodes such as constant and SMI constant are transformed into untagged node such as float constant. Additionally, the type of file changes from T, representing a tagged file, to F, representing an untagged file with input and output types as floats. Next, file untagging handles the output-related node of file node. In this graph, the output of the file node is used by two nodes, checked SMI untagged and the stored tagged field node right barrel node. Since checked SMI untagged node untags the input value, the untagged operation here becomes redundant after the execution of file untagging. Therefore, the checked SMI untagged node is updated to a checked truncate float to int node that takes an untagged value as input. However, the other output using node of the file node has a slightly difference. We can observe that the stored tagged field node right barrel requires a tagged value as input. Therefore, after file untagging, the stored tagged field node right barrel node cannot directly use the output of the file node because the output of the file node has now become an untagged value. To maintain compatibility between input and output values of the nodes, Maglev inserts a tagged operation between the file node and the stored tagged field node right barrel node. This tagged operation ensures that the value after being tagged matches the input type expected by the stored tagged field node right barrel node. In a graph, this tagged operation corresponding to the float box node mentioned in the slide. However, this issue arises with the float box node, which creates a heap number object to wrap the float value as a memory object. This problem lies in the fact that this memory object is saved into a variable property without a right barrel. As a result, the right barrel responsible for tracking this heap number object is missing. During garbage collection, the heap number object may be relocated to a new memory relocation. Due to the absence of the right barrel, the pointer pointing to this heap number object will not be updated during the garbage collection phase, resulting in a dangling pointer. This is the complete proof of concept code provided. Before triggering the vulnerability code, we create a JS object in the old generation and exploit the vulnerability to store a pointer to a young generation object without a right barrel. Next, by involving the garbage collection, we move the young generation object to a different memory location, causing the pointer on the old generation object to become a dangling state. Finally, we use this dangling pointer to trigger a crash. Vulnerabilities that enable remote code execution through right barrel missing are not uncommon, and there are several vulnerabilities related to this pattern. The right barrel missing vulnerability allows us to create an object that holds a pointer to young generation memory, and that object has not yet been recorded in the remembered set. One of the classic methods for exploiting such use after free vulnerabilities is heap spray. Here is the code snippet of exploit. After creating the dangling pointer, we attempt to use a float array to occupy the memory region pointed to by the dangling pointer and perform memory layouts on it. Afterwards, we can utilize this dangling pointer to fake a JS array with controlled length and controlled element pointers. When carefully manipulating heap layout, it is crucial to understand how to use the garbage collection mechanism to manipulate the heap space efficiently. Minor GC moves the object in the young generation to different locations, which can free up the memory region pointed to by the dangling pointer, allowing us to allocate an array in that region. Major GC performs a max sweep garbage collection on the entire heap space to compact the object layout in memory. On the right side is an illustration of the effect when executing the exploit. You can see that before and after garbage collection, the memory address pointed to by the dangling pointer remains the same, but the object type changes from heap number to JS array. This way, we can obtain a JS array object with controlled length and controlled element addresses through the dangling pointer, enabling arbitrary read and write operations to arbitrary addresses in subsequent steps. Before performing arbitrary read and write operations, we need to know what address should be read from or written to. This involves the construction of the address of primitive, which aims to leak the address of an arbitrary object. The construction of this primitive is based on how V8 handles larger objects. When we create a very large JS object, it is not stored in the generational memory, but in a dedicated memory region, specifically for large objects. Interestingly, the address of this memory region is fixed. Therefore, we can modify the element address of the faked JS array to this static address and store the target address to be leaked in the large size array. As a result, the large size array will contain a pointer to the target object, and we can directly read the original value, which is the address of the target object, from the large array through the faked JS array. Once arbitrary memory read-write capabilities to leak arbitrary object addresses within the V8 sandbox are achieved, further exploitation becomes possible. In the slides, the structure of the V8 sandbox is presented. Objects within the sandbox are referred using fixed size offsets rather than raw pointers. Moreover, these objects can be accessed via indesize and in an external pointer table located outside the sandbox. The external pointer table stores pointers to external objects along with the type information to prevent type confusion attacks. It is important to note that the sandbox feature in V8 is still under development and not considered a security boundary. As a result, there exist multiple bypass vulnerabilities that can be exploited to undermine the sandbox security. As the V8 sandbox is still under development, not all pointers are currently sandboxed. For example, code objects may contain unsandboxed pointers that are called during JIT code execution. Overwriting these pointers can be a straightforward method to gain control of the RIP and achieve code execution control. By simply modifying the entry address of the JIT code, it becomes possible to execute the shell code that is concealed within the immediate values of the JIT. Next, we will demonstrate a vulnerability exploitation demo. Okay, first, we try to compile the V8 and then simply run the exploit. After that, a shell pops up and we can execute arbitrary commands. In conclusion, firstly, there may have more change to hunt the vulnerabilities in new implemented JavaScript standard. Secondly, As a compiler that is still under active development, Maglev still has a lot of code that is not yet richly tested and has many interesting features and bugs. Lastly, understanding GC and JIT mechanisms can help us to better handle the vulnerabilities and write more powerful exploits. And that's all. Thank you for your listening.